Hello friends, welcome to Royal Chem classes. Today in this session we are going to discuss about bonding in metal carbonyls. So before starting this session, we should understand what is a metal carbonyl. When a metal, most of the time it will be a transition metal, so we can write it as transition metal or D block metal, bond with a carbonyl group. Carbonyl group means carbon monoxide, C triple bond O, bond with a metal. We call this bond as metal carbonyl group. I am writing it as MC bond. Right? Now this complete compound is known as metal carbonyl. Metal carbonyl. I hope you got it. So to study the bonding in metal carbonyl, first of all we have to check the bonding in carbonyl group. Then it would be easy for us to understand the bonding in metal carbonyl group. So let's check it out. Friends, we know that carbon has 4 valence electrons and oxygen has 6 valence electrons. So we can represent them like this: carbon with its 4 valence electrons, and here I have oxygen with its 6 valence electrons, 5 and 6 1. So here in the carbon monoxide or the carbonyl group, the carbon and oxygen will utilize its first electron to create a sigma bond. So carbon will utilize its first electron and the oxygen will utilize its first electron and will create a sigma bond like this. So we can represent it as sigma bond, and those 2 electrons will be like this. Okay, now the carbon will utilize its second electron and the oxygen will also utilize its second electron and will create a pi bond. So the first one is sigma bond, so obviously the second bond will be a pi bond. So we can represent those 2 electrons here. So this is a pi bond. But you know that in carbon monoxide, you can see there are 3 bonds and we call it as unsaturated bond, right? Because there is more than 1 bond. So how the third bond will create? How this carbon monoxide will create its third bond? Let's see. Look, we know that oxygen can create only 2 bonds, right? And both of these bonds are already generated. Now, how the oxygen will make the third bond? So here, the third bond is not a pi bond, it's a coordinated bond. How is it forming? The oxygen in the carbon monoxide will donate its lone pair of electron to the carbon and will create a coordinated bond. So the third bond, we can represent it with an arrow line, because when you are representing a coordinated bond, that should be a arrow-headed line. So we can write it as, so these 2 electrons will get removed from here because it's utilized for the bond, that's the third bond. That bond we can represent with an arrow line like this because it's a coordinated bond. So here this is carbon and now this is oxygen, and these are the 3 bonds. The first bond is sigma, second bond is pi, I am representing here, and the third one is a coordinated bond. So this is the bonding in carbon monoxide or carbonyl group. Now check, the carbon has 1 lone pair of electron, lone pair. Also, the oxygen has 1 lone pair of electrons, right? Now, the carbon will utilize its lone pair of electron to bond with metal when they are creating a metal carbonyl compound. So let's see how this carbonyl group is making a bond with a metal. Before that, I will introduce your orbital. Look, here we have sigma bond and pi bond, right? So obviously there will be pi star orbital, right? Because we know that as per both molecular orbital theory, or you can say MOT, we know that for every sigma bond there will be a sigma bonding molecular orbital, there will be a sigma star anti-bonding orbital or ABMO, right? So for every pi bond, this is pi BMO, there will be a pi star BMO, right? Pi star ABMO. Pi star ABMO. So here in the carbonyl group, since we have a pi bond, there will be pi star orbitals. And we know that these pi star orbitals will be empty because there is no electrons in pi star orbital as per the molecular orbital configuration. If you check out the molecular orbital configuration of carbon monoxide, you can see that the pi star orbitals are free. So the pi star orbitals of this carbon monoxide group will be empty. I am removing this lone pair label I hope you understood that. So I'm just keeping the pi star orbitals. Okay, look, in the carbon monoxide we have sigma and pi bond, so the pi star orbital will be there. I am drawing that pi star orbital like this. This is the pi star. Sorry. So this is the pi star of Cu, carbon monoxide bond. Okay, pi star C triple bond O. Okay, pi star C triple bond O. I hope you got it. Now let's take the bonding in metal carbonyls. Look, here we have a metal because the metal carbonyls should have a metal, right? And most of the time this metal will be a transition metal. Of course it is a transition metal and it will have d orbitals around the metal like this. 1, 2, 4. Okay, so now the metal has its d orbitals around it, and you can see that few orbitals are filled and few orbitals are vacant. So we can call these as filled d orbitals, and here we can call these orbitals as vacant d orbitals, right? Now let's take the carbonyl group. So here I have a carbonyl group C, triple bond O, sigma pi and a coordinate bond, and I have already shown you the pi star orbitals around the carbonyl group. So this is called pi star C triple bond O, right? Look, in the pi star orbital also it's empty, right? So you should write it as empty pi star of carbonyl group. Fine. Now what will happen? We know that the carbon has a lone pair of electrons around it, and the oxygen is also having a lone pair of electrons, a single lone pair of electrons around it. Okay. Now what will happen? So to make a bond with the metal, the carbonyl group will share its lone pair of electrons into the vacant d orbital of the metal, like this. This is not a mutual sharing. It's like a complete sharing of a pair of electrons from carbon to the vacant d orbital of the metal, like this. So what will happen? These two electrons will get transferred to the metal, vacant d orbital of the metal, and it will create a coordinate bond with the metal like this. So you can keep those two electrons over here, right? So this is called sigma donation of carbonyl group. You can write it as sigma donation of carbonyl CO group. Okay, because it's creating a sigma bond between carbon and metal, right? Also, this bond is a coordinate bond because it's transferring a pair of electrons from the carbon to the metal. It's not a single electron; it's a pair of electrons. When a pair of electrons transfer from one group to another group, we call it as a coordinate bond. So here the first bond through sigma donation of CO group is a coordinate bond. I hope you got it. Now, is there any possibility of having a second bond? Yes, there is a possibility, because look, in the metal you can see that there are filled d orbitals, right? And it has electrons in it. You can see here there are electrons, right? So what will happen when the carbonyl group bond with the metal through sigma donation? The metal will have a tendency, if the metal is having a d electron in its d orbital, the metal will donate its lone pair of electrons to the vacant pi star orbital of the carbonyl group. To do what? To have a second bond. So the carbonyl group, not the carbonyl group, the metal will donate its lone pair of electrons and will create a second bond with the carbonyl group. So we can draw it like this. Also it will connect its bottom lobes as well. Write this. Okay. Don't get confused. This is a single orbital, right? So what it will do? It will create a bond. So we can keep those two electrons over here. This is another bond. This is the second bond in metal carbonyl bonding, and this bond is known as pi bond. And this is happening due to the pi backbonding of This is happening due to the, first of all, I will call this donation as pi donation of metal. You can say pi donation of metal. Pi donation of metal. Why we are calling it as a pi donation of metal? Because it's resulting in the formation of a pi bond. Resulting in the bond formation of a pi bond. So we call this donation as pi donation of metal, and the bond is a pi bond. So the first bond was a sigma bond due to the sigma donation of carbonyl group to the metal. Now the second bond is a pi bond due to the sharing of a pair of electron from metal to the vacant pi star orbital of carbonyl group. So I hope you got it. This is the bonding in metal carbonyl group or metal carbonyl compound, you can say. So this complete bonding will happen together simultaneously. So we call this effect, or we call this bonding as synergic effect. Synergic effect, or you can say synergic bond, right? What is it doing? It will strengthen the bond between metal and carbon. But it is not often. There are some conditions to happen in this particular pi back bonding. So there are three major factors which will affect the pi back bonding in metal carbonyls. So let's check the factors affecting metal carbonyl pi back bond. Friends, there are three major factors which will affect the bonding or pi back bonding in metal carbonyls. Those are the charge of the metal, charge of complex, and number of d electrons in the metal. We can check one by one. First of all, we can start with the charge of the metal. Look, I have two, here I have two metal carbonyls, or you can say metal carbonyl compounds. First one is M plus CO, M plus CO, and the second one is M2 plus CO. Which one do you think will have more pi back bonding? Let's check it out. Look, here in the first case, the metal is in +1 oxidation state. Metal is in +1 oxidation state. And in the second one, the metal is in +2 oxidation state. +2 oxidation state. +2 oxidation state. So what will happen? Look, when the oxidation state or the charge of the metal increases, the number of d electrons decreases, because we know that to do the pi back bonding or the pi donation of the metal, to have the pi donation of the metal should have more number of d electrons, right? So when the charge increases, because metals are electropositive, when the positive charge of the metal increases, the number of d electrons in that decreases, right? So when the number of d electrons decreases, when the positive charge increases, the electron density around the metal decreases. So you can say that charge of metal, charge of M means metal increases, charge of metal increases. What will happen? Electron density around the metal, will decrease, right? Electron density around the metal decreases. When the electron density around the metal decreases, the pi back bonding will decreases, because for doing the pi back bonding, the metal should have high electron density, or it should have more number of electrons or more number of d electrons around it. So we can say that here the pi back bonding, order of pi back bonding will be, the first one will be high pi back bonding. The probability of pi back bonding will be more in the first compound than the second one, due to the increase in the charge. I hope you got it. So we can say that charge of metal is inversely proportional to pi back bonding, right? Pi back bonding. Charge of metal is inversely proportional to the pi back bonding. Now let's check the second factor, that is the charge of the complex. Let's check it. Friends, to check how the charge of the complex will affect the pi back bonding, we can take these three complexes. Why I am taking complexes? Because metal carbonyls are coordination compounds, right? So here I am taking three metal carbonyl complexes. Look, in the first one, the charge of the complex is minus, -1 you can say. In the second one, it's a neutral complex, and in the third one, it's a positively charged complex. So here it is a anionic complex, you can say. This is an anionic one. This is a neutral one. This is a neutral one. And this is a cationic one, right? Cationic one. So what will happen? What will happen? Let's see. Look, when the charge on the complex is negative, the electron density around the metal increases, because we know that negative sign indicates the presence of electron, right? So when the charge on the complex is negative, we can say that the charge density of this complex, electron density of this complex increases. But when the charge on the complex is positive, that is a cationic complex, the charge on the complex or the electron density on the complex decreases. So we can say that the electron density is more in MCO X times minus than MCO X times plus. So obviously we know that electron density, this is a major point, electron density is directly proportional to pi backbonding. Electron density is directly proportional to pi backbonding, right? So the electron density will be more here, and here the electron density will be less. And the neutral will come in between these two. So as per this relation, we can say that the charge on the complex, when the charge on the complex is negative, the pi backbonding in metal carbonate increases. So here the order of pi backbonding will be MCO X times minus greater than MCO X times, which is greater than MCO X plus. I hope you got it. So this is the order of pi backbonding. So the relation will be when the charge of the complex is negative, or you can say negative charge on the complex increases pi backbonding in metal carbonates. I hope you got it. So the third factor is number of d electrons. Number of d electrons we already discussed in the first point, charge of the metal, because when the number of d electrons, number of d electrons around the metal increases, the electron density increases. So the number of d electrons is directly proportional to pi backbonding. This is the relation. Right? In the charge of the complex, we can write the relation as negative charge on the complex increases. What will happen? Pi backbonding increases. Pi backbonding in metal carbonates increases. So these are the three major factors which will affect the pi backbonding in metal carbonates. I hope you got it. Friends, by this we can conclude today's session. I hope you guys got a clear idea about bonding in metal carbonates. Thank you for watching. Keep learning with Royal Chem.